This video will cover how to calculate the pH of a weakly basic solution. So if we have a weak base, much like when we have a weak acid, it doesn't completely dissociate in solution. So we don't get as much OH minus in solution as there is the concentration of base. So another way to say that is the concentration of our base is not equal to the concentration of OH minus in solution. And if I have a weak base, then the amount of OH minus in solution is going to be less than the concentration of the actual base. And because these are not equivalent, I'm going to need to do an ice table to figure out how much of that OH minus has dissociated in solution. So let's look at an example of a weak base, and I'm just going to do kind of a generic base. So we'll do some base, aqueous, plus water, and that's a liquid. And I put equilibrium arrows because this is a weak base, is going to give me BH plus, so my protonated base, it has accepted a proton, plus OH minus aqueous. So remember the definition, one of the definitions of a base is that it generates hydroxide in solution. So I'm going to add a little lone pair to my base here. Remember that a base is a proton acceptor and an electron donor. And so I'm going to have an arrow starting at this lone pair of electrons and ending on the proton that it's accepting. And that's how I get this BH bond right here. And then I'm going to have this bond between the oxygen and the hydrogen. Those electrons will go onto the oxygen as a lone pair. And that's how I get this negative charge right there. So if I drew in the lone pairs on my oxygen, it would have 1, 2, and 3 lone pairs. So much like we have a Ka for an acid, we have a Kb for a base. It's going to be products over reactants like all of our Ks have been. So we have the conjugate acid of our base times the concentration of hydroxide ion all over the concentration of my base. Now remember, we're leaving water out because it's a pure liquid, so its concentration doesn't change provided there is some water left in solution. So let's say that I have a 0.1 molar solution of a weak base, and I'm just going to call it B, okay? And I know that its Kb is equal to 4.3 times 10 to the negative 5. Okay, so what I want to do is set up my ice table. So I'm going to write out my reactions. So I have my base that reacts with water to give me the conjugate acid of the base, BH plus my hydroxide ion. So I'm going to draw a line through the water because I don't want to do anything with that because it's a pure liquid. So initially I have 0.1 molar. We'll put a 0 in front of that and up here too so it's easier to see. And I don't have any of my conjugate acid and hydroxide. So I'm assuming that when I first make the solution, none of it has dissociated. I'm going to let it sit for some amount of time, and then some of that base is going to dissociate. So because some of it is going to dissociate, I'm going to put minus x there, and then plus x here, and plus x here. So at equilibrium, I will have 0.01 minus x base left in solution, x amount of conjugate acid, x amount of hydroxide. So now I can solve for x. So my Kb from before was 4.3 times 10 to the negative 5. And that is going to be equal to the concentration of my products over my reactants. So in this case, I had x amount of conjugate base and x amount of hydroxide, so x times x, or x squared, over the concentration of my base originally, which was 0.1 molar minus x. So when I do this, then I can solve for x, and x is equal to 0.00205 molar. Okay? Now, when we do an ice table with an acid, this is equal to the concentration of H plus in solution. So I can go directly from there to my pH. But in this case, this is equal to the concentration of OH minus. Okay, so my concentration of OH minus is equal to 0.00205 molar. So there's two ways that I can do this. One way is to take the negative log of that number, and the negative log of OH minus is equal to the POH. And so then I can go from my POH to a pH. So we'll go to the next slide and I'll do the POH of this solution. So for this solution, the POH is equal to the negative log of 0.00205 molar OH minus, which is my concentration. So my POH is equal to 2.687. Now, we don't really use the POH scale as frequently as we use the pH scale, but I can get back and forth because pH plus POH is equal to 14. So if I rearrange that, I can say 14 minus my POH equals my pH. So I just took my POH over to the other side. So in this case, 14 minus 2.687 is equal to the pH of my solution, and that is equal to 11.31, which is what we would expect. So if you're paying attention here, you'd notice if you get a number that is 2.687 for a basic solution, that does not coincide for a pH, right? Because a pH of 2.687 would be a very acidic solution. It makes sense to have a pH of 11.3 for a basic solution. So the other way that I could have done it, though, is I could have used Kw. So if you remember, Kw is equal to the concentration of OH minus times the concentration of H3O plus or H plus. We've been using those sort of synonymously. Kw is 1 times 10 to the negative 14 molar. In this case, I have a concentration that I know of my hydroxide ion, and so my only unknown is my H3O plus. So in this case, I can solve for the concentration of my H3O plus, which is equal to 4.878 times 10 to the negative 12 molar. And then I can take the negative log of that to get the pH of my solution. So the negative log of 4.878 times 10 to the negative 12 molar. And if I do it this way, this is my pH, and again I get 11.31. So either way, you're going to get the same answer. You can go from a POH to a pH using the equation we used previously, or you can use Kw to go from a concentration of OH minus to a concentration of H3O plus, and then take the negative log of that to get a pH.